for the case that the material is general anisotropic material. Okay. Here I try to specialize to isotropic case. You know that, okay, if the material is homogeneous and isotropic, we need only two constants, okay, to completely describe the behavior of the material. Okay, and we know that if the body is homogeneous, so the material constants are not a function of position. So the compatibility condition in terms of stress can be simplified. And that kind of condition we call Beltrami-Mitchell equation, right? So in this case, we will use Beltrami-Mitchell equation as one of the governing equation of this problem. Okay. So this is the form of Beltrami-Mitchell equation for isotropic materials with constant material properties. Okay. So the final form of boundary value problem is given here. Okay, we want to find stress field sigma that satisfy two sets of equation. The first one is the equilibrium equation, right? So stress here have to satisfy equilibrium. It have to be in equilibrium with the prescribed body force field. Okay, or you have to satisfy sigma I j comma j plus bi equal to 0 at every point in the body. Okay, and also stress field have to generate the displacement field, or the displacement field have to exist, right? So to confirm that stress field have to be compatible, or stress have to satisfy Beltrami-Mitchell equation, so that ensure the existence of the displacement field. So this is two governing equations, okay, for the stress field. So these two sets of equations have to be satisfied at every point x, at every point x in the body. Okay, they cannot be satisfied just only some points in the body. To be the solution, stress have to satisfy these two sets of equations at every point inside. So on the boundary, stress, the given stress field, or the one that you want to determine, have to satisfy the condition at the boundary, every point on the boundary. So we have two parts of the boundary, right? So on the surface SU, we know the displacement field, right? So we know U0. So in this case, stress field have to generate the displacement field that satisfy this condition at every point x on the surface SU. So here I just simply express the displacement field in terms of stress, because I cannot write down the expression explicitly. Okay, there is no closed form expression of stress, of the displacement in terms of stress. The reason is we need to perform the integration, right? So strain displacement relationship that that one cannot be solved to get a closed form of the displacement in terms of strain. So this result in the final form that I expressed here like this, because the displacement cannot be directly expressed in terms of stress. So I just simply write down that function form like this. So to check this boundary condition, you need to confirm that stress satisfy that Beltrami-Mitchell equation. So if that one is satisfied, you check that one first. So now you don't need to worry the existence of the displacement field. Okay, so you can always integrate strain displacement relationship to get displacement field. So this function form exists whenever that equation is satisfied. Okay, so we need to confirm this condition at every point x. Okay, on the surface SU, and on the surface ST. On that part, it's very simple to verify because we know we use stress as a key unknown. So once we solve stress from these two equations, so now we can generate traction. So we just simply take sigma multiplied by n, the unit normal vector at point on the boundary, and we set that, or we verify that with the prescribed traction. If this condition is satisfied, now we can say that stress satisfy the traction boundary condition on the surface ST. Okay, so this the final form of the boundary value problem formulated in terms of stress field. And this one is applicable only for the case of homogeneous and isotropic materials. The reason is the Bell-to-Mitchell equation that I show you here. So this is this is applicable only for the case of homogeneous and isotropic material. So if the material is not homogeneous or it's not isotropic, you can move to the formulation that I showed you last time, the one that is more general, because we can just simply replace the compatibility condition or the Bell-to-Mitchell equation here with the one that is more general, that we express in terms of stress with general elastic compliance. Okay. Do you have any question here? We done with the formulation of the problem, the same problem, but I show you three different formulations. One with general, or one with all field quantities, all field unknown quantity as a key unknown, right? So we formulate in terms of stress, strain, and displacement field. That is the first one. That is the original one. Okay, and then I also show you the formulation in terms of the displacement field. That one is simpler in terms of the number of coordinate equations and also the number of unknowns, right? Okay, and the last one that I just show you here. So we formulate the problem in terms of stress field. Okay, so for the final one here, what if we already determine stress from this formulation, or we solve this formulation and get stress field? How can we obtain the remaining field? So obtain strain is very simple, right? Because you know that, okay, we can express strain in terms of stress. Okay, so this is the general expression for general linear material, that we can multiply elastic compliance to stress field. We can always get strain field. So once you solve stress here, okay, once you got this stress field, you can simply plug it in here. Okay, you plug in stress field in this expression, you can get strain. This is quite simple, right? Because it's just plugging in without solving any equation. The one that is more complicated, the one that related to the determination of the displacement field. Okay, from strain here, you have this kind of relationship, if you remember. So strain is simply epsilon ij, sorry. Okay, so we have epsilon ij equal to 1/2, right? Ui comma j plus uj comma I. So whenever you confirm that the given stress or the one that you solve from this equation. So if stress is solved from these two set of equation, so now you confirm that this one is satisfied, right? Because it satisfied that equation. So you solve it from here. So that condition is satisfied. What does it mean? So this one is satisfied. It confirmed that strain generated from that stress is compatible. So once you have the compatible strain, when you plug it in here, this equation is integrable. Integrable in the sense that you can always solve this partial differential equation to get the displacement field, right? So the displacement field exists. So now, how can we get the displacement field? We just simply use using the knowledge in differential equation. We can solve this set of equations to get the displacement field. I will show that procedure in the next in the third lecture. I will show you how to get the displacement field whenever we know the strain field. So based on this information, okay, we can get all field quantities, right? Once we solve the key unknown stress, then we can post-process for strain and for the displacement field, okay? I will show you the example here, one example. I will try to formulate the problem in 3 ways, as I shown you before. Okay, I would like you to get some idea, okay, how to get those formulation for some specific problem. In this case, I look at a bar, okay, a bar of length L, and the cross-sectional dimensions is given here. So the width of the cross-section is 2b, and the depth of the cross-section is 2d. Okay, you can think about this as the beam. Okay, and I have I restrain the displacement completely at the left end, or you can think about the fixed support here. Okay, so I prevent the movement completely at that end, or every point on this end. So we just simply restrain against the movement in all directions. So the displacement is 0. Or we can say that the displacement is known equal to 0 on the surface S1. Okay. At the bottom here, let's say that, okay, we have a rigid substrate here. Rigid means what? Okay, this one cannot deform. Okay, it's rigid and it's frictionless. The body that I am interested in here just simply rests on this rigid substrate. Okay, and the surface here is frictionless. It means that there is no friction generated when you apply the force to the body here. So the only thing that we have in terms of the force at the contact surface here. So we have only the normal component of the traction. So the shear component is 0 because it's frictionless surface. Okay. I apply the shear traction, the uniform shear traction tau 0 at every point on the surface S2 or at the right end. Okay. On that surface, I specify uniform shear traction. Okay, tau 0 here is prescribed. Okay, and at the top of the beam, okay, at the top here, every point at the top, we know the traction. We apply the pressure, the uniform pressure equal to P0. Okay, pointing downward like that. Okay. On the two side faces, okay, we have two side faces here. Okay, I use the symbol S5 and S4. S5 and S6 to represent the side face of the body. Okay, so let's say that on the side face, on both of them here, we know the traction and they are equal to 0. Or I can say that the traction, we have the 0 traction prescribed at every point on the side faces. Okay. So this is a problem that we are interested in. Oh, sorry, I know one more condition. So I know that, okay, the unit weight of the bar, let's say that we have the gravitational force field pointing downward like this. And I give you the unit weight of the bar of the beam here equal to the constant value gamma. Okay, so the unit weight is constant throughout the body. Okay, so that is the information that we have here. So I would like you to formulate the problem, formulate the boundary value problem in several ways. Okay, using the form that I mentioned before. Okay. Before we formulate the problem, we need to understand the data of the problem first. Okay, we need to be able to identify all the known data. Okay, the prescribed data of the problem. What do I mean by that? I need to identify all the information like the geometry, okay, loading condition, boundary condition, material properties. All those information must be identified first, because that kind of information will enter the formulation somehow to make sure that, okay, the formulation that we will get here is specific to the problem that we are interested in. Okay. So the first information that I mentioned here is the geometry. So we need to know the geometry of the body that we are interested in, right? And here we look at the bar here, okay? So the bar that we look at here occupies a region, okay, in Euclidean space. So for convenience, I choose the coordinate system with the origin at the centroid of the section at the left end. So the origin is here, okay, at the centroid of the cross section at the left end. And I shoot x1 axis point in this direction, okay, and x2 direct in that way, okay, and x3 can be obtained from the right hand rule, right? Okay, so x3 pointing in that direction if you look in terms of the cross section. Okay, that is a coordinate system that I select here in the formulation. So based on that coordinate system, I know that the body that I am interested in can be expressed in terms of a region in the Euclidean space. And this is simply the Cartesian product of the interval 0L minus D and D and minus B and B. Okay, that is simply the region of the body. Okay, and also we have the boundary. If we look at the body carefully, so the boundary can be decomposed into 6 subsurfaces. Okay, S1 to S6. S1 is simply the boundary associated with the left end. S2 associated with the right end. S3 and 4. S3 is associated with the top of the beam. Okay, and S4 is S3 is the bottom of the beam, and S4 is the top of the beam. And S5 and S6 represent the side faces of the beam. We also know the information based on the geometry that we have. We know the unit normal vector on the unit vector on each subsurfaces. On the surface S1, the outward unit normal vector is simply -1, 0, and 0. And the components that I talk about here refer to selected coordinate system, right? So we have x1 pointing in that way, x2 pointing up like this, and x3 normal to the 2 here. So in this case, you know that the unit normal vector point in that direction, right? So that is your n, the outward unit normal vector. So in terms of the components, based on the chosen coordinate system, so I have n equal to -1, 0, and 0. So that one is known a priori, right? We know from the geometry. Okay. For the surface S2, okay, n is simply 1, 0, 0. That is clear because this is n, right? For this case. Okay. And we can do exactly in the same way. We can list, n for all surfaces. For example, S3, the bottom surface is simply 0, -1, 0. And S4, we get 0, 1, 0. And S5 and S6, we get like that, okay? That should be clear to you, right? Okay, so this is what I mentioned to you, that we know the geometry of the body, okay? How about the body force field? This is associated with the remote force that we prescribe at the beginning. So we know that, okay, we have the gravitational force field pointing downward, right? Okay. So, and we have the prescribed constant unit weight of the bar equal to gamma. So in this case, I know that the body force field at every point here will point in that direction, right? So the body force field have the non-zero components in the negative x2 direction. Okay, so I can write that thing down explicitly. B, the vector B for this problem is simply 0 minus gamma and 0. Okay, and gamma here is a given unit weight of the material. Okay, is that clear to you?
Yes, sir.
The reason that we get the negative sign here, because like I told you, the gravitational force field, pointing in, downward like this. So we have the negative value here. Okay. How about the material properties? I told you before, from the problem description, we know that, okay, the body here is made of isotropic material, right? I forgot to mention about that. Let's say that, okay, the beam here is made of homogeneous and isotropic material. I gave you the constant, okay? Young modulus and Poisson ratio, okay? So that have to be given, okay? And in this problem, I gave you two constants, Young modulus and Poisson ratio. Keep in mind that, okay, in your formulation, you have to express the constitutive law in terms of these two constants, okay? Because these are given information, okay? So when we formulate the problem, okay, or we try to write down the equation relating strain and strain, make sure that the relationship there is expressed in terms of Young modulus and Poisson ratio. Okay, if you write out the expression in terms of like, for example, Lamy constants, you have to show or give the relationship of the Lamy constants in terms of Young modulus and Poisson ratio, because these are data that given for this problem. Okay, what else do we have here? The boundary conditions, right? What kind of boundary conditions that we have for this particular problem? So if we take a look at each subsurface, right? We have S1, S2, S3, S4, S5, S6. Okay, for each subsurface here, we know the condition, right? I told you before that any point on the boundary, we need to know displacement or traction, one of them. Okay, only one of them. If we look at S1, I told you that, okay, the body is fully fixed at that end. That means what? At every point on the surface S1, you know the displacement field equal to 0. So in this case, I can say that we know U0. U0 is the prescribed displacement, okay, at part of the boundary. So in this case, we know U0. And U0 is simply 0, 0, and 0, because every point on that surface is fully fixed against the displacement. Okay. How about the surface S2? On that surface, we don't know the displacement, right? but we know the traction. And the traction that is non-zero, we know traction in all direction. But the only one that is non-zero is a traction along negative x2 direction, right? We don't have traction in that direction. We don't have traction in x3 direction. But we know that those two components are zero. So traction is fully prescribed on that surface. So now we can write down the traction like this. Okay, T0 is simply 0 minus tau 0 and 0. Traction in 1 and 3 components, or in 1 and 3 direction are 0. We know that they are equal to 0. But the one that is non-zero, we have the prescribed value equal to tau 0. The negative side here just implies that the direction of that applied traction is opposite to x2, right? Okay. How about S3? If we look at point on the surface S3, what do we know here? I told you that the box here or the substrate here is rigid, right? It means that it cannot move, it cannot deform, right? Okay, that one is fully rigid. And also the surface of this substrate is frictionless. Okay, what does it mean? So when you apply the force to the body here, to the beam here, the contact point on the contact surface here can move freely in that direction, right? Because we don't have the restraint from the friction. Okay, so we can say that if we look in terms of the movement in that direction and the movement in that direction, we don't have any restraint against the movement. What does it mean? So we don't have the force. We don't have the force generated in the two directions here as well, right? Because it's frictionless. But if you look at the movement in the vertical direction, in that case, the box here or the substrate here is rigid. So now it will not allow the body to move up or down. Okay, so in that case, we know the displacement component in that direction, but we don't know the force or the traction in the normal direction, right? Because that force is unknown a priori. The magnitude of the force depends on how you prevent the movement in that direction. Okay, we cannot know the displacement and the traction in that direction at the same time. But in this case, because we say that the substrate here is rigid, so the movement is zero in the vertical direction or in the direction normal to the surface here. So on the surface S3, we can say that we know the mixed conditions because we know the traction equal to 0 in x1 and x3 direction. But in x2 direction, we know the displacement field, right? We know displacement equals 0 in x2 direction or in the direction normal to the surface here. Okay, so now I can write down the boundary condition for this surface. We know T10 and T30, okay, equal to 0. And we know U20 equal to 0. Okay, is that clear to you? So I call the mixed conditions because we know both. I shouldn't say we know both. We know traction, the two components of the traction, and we know one component of the displacement field. Okay, which is different from the one that I show you here. Okay, S1 we say that we know the complete. We completely know the displacement field. For S2, we completely know the traction, but this one we know the mixed condition. Okay, These two components, we know traction, and that component, we know displacement. Okay. Okay, for S4, that is clear because we apply the loading on the top of the beam. So we know the traction in that case. So in this case, we apply the traction only in the direction downward here, right? So in this case, we know T2, right? T20 is simply minus P0. And P0 here is the magnitude of the pressure that we apply here, okay? And T10 and T30 are 0, okay? And we can say that the traction is completely known for this surface S4. How about S5 and S6? S5 and S6, they are traction free. Or we can say that the traction are prescribed equal to 0 on those two surfaces. Okay, so now I can say that S4 and S5 and S6, the traction is known, but vanishes, right? We can say that T0 is 0, 0, 0 for both surfaces. Okay, these are boundary conditions of the specific problem that we are interested in. Okay. Is that clear to you? So when you do your homework, the first homework, I suggest you to list all the known conditions at the beginning. We need to list all information that we have for that specific problem. And then we will use that information in the formulation. I will show you later here. Okay, the first formulation, I will try to formulate the problem in terms of displacement, strain, and stress. Okay. This is the simplest one because I will use all the information that we have before, right? We use all unknowns as the key unknowns. And we will use all field equations that we have as the Copenhagen equations. Okay. So this is the formulation that I got. I want to find the displacement field U, strain field epsilon, stress field sigma. That satisfy what? All field equations. If you remember, we have 15 equations for the 3D case, right? So we have sigma I, j, comma j plus bi equal to 0. That's equilibrium equation. We have epsilon I, j equal to 1/2 ui, comma j plus uj, comma I. That is strain displacement relationship. And we have a Hooke's law for isotropic material. And I have sigma ij in terms of epsilon ij expressed in terms of Young modulus and Poisson ratio. But if you don't like the expression of stress in terms of strain that relating by lambda and mu, let's say that you prefer to express the stress-strain relationship in terms of the Lamé constant. Don't forget to express those Lamé constants in terms of Young modulus and Poisson ratio as well. Because if you take a look at the information of the problem here, I gave you E and Poisson ratio, not lambda and mu. If you write down equation in terms of those two constants, you have to express those two in terms of E and Poisson ratio. Okay? Make sure that you are specific to the information that given a priori. Okay? So here, I want to find the displacement, strain, and stress, satisfy all field equation like this. And also satisfy, okay, I forgot to emphasize here. So we need to make sure that all the field equations here are satisfied for every point X in the body, omega. And you can see that the information of the geometry of the body come into play here. So you have to be specific to the body that you are interested in. not any general body. This is the one that you are interested in, right? This body, okay? This body occupy the region here, right? Okay, and you can see that if you write this thing down like this, the body force here is have to be specified as well. At the end, I will write down what B is because B is known here, right? And also this equation, you can see that I try to write down in a way that involve the quantity that I known at the beginning, right? We know the material property of Young modulus Poisson ratio. So when I write this thing down, I have to be specific to the problem here. Okay. I need to satisfy the boundary condition as well. In the formulation, you have to provide the boundary conditions. Okay. If you take a look at the surface S1, on the surface S1, we know the displacement field. So the boundary condition take this particular form, right? We know U1, U2, and U3. So I set U1 and U2 and U3 equal to 0 because this one is U0. Don't be confused here. That one is U0. So we need to set U equal to U0 at point on the surface. So that one is U, not U0. Okay. For the displacement U to be a solution of this problem, the value of this U at point on the surface S1 have to be equal to U0, and U0 here is a prescribed value that I mentioned before. Okay. For the surface S2, we know the traction, right? So the traction T1, T2, and T3 are completely known there. So I will set the value of the traction in terms of, I set that equal to the one that we prescribed. So this is T0, okay? And on the left-hand side here, we just say that, okay, T1, T2, T3, I write down that one in terms of stress. What does it mean? Because if you don't give any relationship between traction and stress, no one gonna know how to check this condition, right? Because if you take a look at the formulation that we have here, the key unknown that we have stress, not traction. So if you just simply set T1 equal to 0, T2 equal to minus tau 0, and T3 equal to 0, no one gonna know how to check that condition, right? How to verify that condition, because T here is not the key unknown. But we know that T and sigma are related somehow, right? If you remember, we know that traction is simply stress multiplied by N. So this is the connection that I talk about, okay? So now if you write down the traction in terms of stress like this, using this relationship, so now you have a way to check this condition for the surface S2, right? So basically you just take stress multiplied by N and you verify with these quantities. And N for S2, I showed you before, right? For this surface, we know that N equal to 1, 0, and 0. So basically this is the way that allow you to check this condition. Okay, now we look at S3. S3 is a little bit different here because the first and the third component, we know the traction. The first and the third direction, we know traction, and the and the second direction, we know displacement. So we have the mixed condition. So when we verify, if we want to verify the condition on the surface S3, so we say that, okay, U2 have to be 0, right? We have to check that U2 have to be 0, okay? But for T1 and T3, that have to be 0 too, okay? And T1 and T3 here have to be linked with stress somehow. I will show you at the end, okay, using this formula, okay? And N for this surface is simply 0, minus 1, and 0, okay? And S4 and S5 and S6, I can do exactly in the same way as S2, because on the surface S4, 5, and 6, we know traction completely. Okay, S4 and S5 and S6, T0 is 0, right? They are 0 here. And for S4, T2 is not 0, but T1 and T3 are 0. Okay, you can see that all the information that we know have to be used here in the formulation, and also for the N as well. Okay. If let's say that, okay, I am done with the formulation like this, without showing anything else. Let's say that I have this kind of formulation like this. I would say that, okay, this is not a complete formulation. If I didn't provide anything else except this, what happened to the formulation here? If you give this formulation to your friend and ask them to solve the problem, they cannot solve this problem, because some information is missing here. What kind of information is missing here? B, right? I didn't say anything about B for this problem. So B there, if I didn't provide any information in this formulation, your friend cannot solve the problem because they don't know what B is, right? So I need to provide that information as well. So here I say that B1, B2, and B3 are simply 0 minus gamma and 0. So that is the information that I know from from the problem, right? That condition is known a priori. Okay. What else? This one have to be provided as well, right? If you don't provide this to your friend, they don't know how to check the condition like this. For example, how can they check this condition if they don't know this relationship? Okay, because once you solve for stress, if you want to verify this condition, you don't have a way. If you don't have the connection between T and sigma, then you have to provide this information, right? Traction can be expressed in terms of stress based on that Cauchy formula. You just simply take stress component like this and take the matrix, the product between the matrix here and the vector of our unit normal to the boundary, right? So you take the product between the two here. Now you can get traction. So then you can verify this condition. So if you don't have these two information, I would say that, okay, the formulation here is not complete. Okay. Do you have any question about this part? I expect to see the solution that you are doing now for the homework assignment 1. Okay, like this, because I asked you to formulate the boundary value problem using all unknowns like this as well, right, in your homework. So try to do like what I show you here. Provide all the information that is essential to and specific to the problem that you are interested in. Okay. Any question here? No? No question at all. So let me move on. If I want to formulate the problem, the same problem here again, but I will choose only the displacement as the key unknown. So I can say that the boundary value problem that I would like to formulate here is the displacement based BVP. Okay, the displacement based boundary value problem. Okay, in this case, I will use the governing equation in terms of the displacement field that I call the Navier equation, right? And this is the Navier equation that I have. Okay, I expressed for this special case. This is not the Navier equation for the general case because I try to be specific to the problem that I'm interested in here. You know that the body is made of isotropic material, and then the material is homogeneous as well. So this is the form of Navier equation for homogeneous and isotropic material. Okay. But one thing that you have to be careful. Navier equation that I show you here is expressed in terms of Lamé constant. That's not the data that I specify or I gave you, right? For this problem, I gave you E and Poisson ratio, right? I need to tell, or I need to express somehow in the formulation to link between mu and lambda and the known data, okay? Because if you just simply express the equation like this, when you try to solve the problem, you don't know what the value of mu and lambda are, right? If you don't have this kind of relationship, okay? Keep in mind about this as well, okay? Also, you know that, okay, part of the boundary here, we know traction, right? For example, on that surface, we know traction, on that surface, we know traction, on that surface, we know traction, and that surface, we know traction. And part of this, you know, not part of, some component, okay, of the known quantity here are related to traction. But we shoot the displacement at the key unknown, right? So how can we verify, or how can we check those kind of boundary conditions? So we need to be able to express traction in terms of the displacement field. And I showed you before, right? I show you how to derive traction in terms of the displacement. I gave you the final expression as well, if you remember. Okay, so that is the expression that I talk about. So I have to write down traction as a function of u, right? And that form is given explicit here. Okay, this is the explicit form of that function. Okay, whenever you know displacement field, you can simply plug in this formula. Now you get traction. And then you can use that traction to verify the boundary condition, for example, on the surface S4. Okay, but if you don't have this relationship and you didn't provide or supply your formulation with this relationship, now you cannot verify the condition, okay, like the one on the surface, the one on that surface, because the key unknown is the displacement field. Okay. This is the final formulation that I have. Okay. I would like to find the displacement field U. Okay. That satisfy what? This equation. Satisfy the Navier equation for every point X in the body. Okay. Is that clear to you? Okay. And don't forget that the body here have to be specific to the one that the one that we interested in. Okay, that is information of the body. How about the boundary condition? We have to include all the boundary conditions. The first one is easy on the surface S1 because the condition we know here is the displacement. And the displacement is a key unknown in this formulation. So this is straightforward, right? Because we can just simply verify directly because U is the key unknown. So we just simply set that U1 and U2 and U3 are equal to 0 on that surface because we have the fixed support here. Okay. How about the surface S2? the surface S2 here, if you remember, if you go back to the previous formulation, I write down traction in terms of stress because stress is the key unknown, right? But here, stress is not the key unknown anymore. So you cannot just simply write down traction in terms of stress. If you write down in that way, you don't have a way to check here because U is a key unknown, right? Okay, so we need to express traction in terms of the displacement. And then we verify with the prescribed traction here. And I need that kind of relationship to convert displacement into traction. And then I check that condition. Okay, so this is the boundary condition on the surface S2. This part is still the same, right? This part is still the same as the previous formulation because it's the prescribed data, that part as well. But the one that changes here, right? Because for this case, we need to express everything in terms of the displacement, the key unknown that we select at the beginning, okay? And for the surface S3, we do exactly the same way. The second component here, okay, we know U2, right? In the second direction, we know U2. So in X2 direction, we know U2. So we just simply set U2 equal to 0 there. But for X1 and X2 direction, we know traction. So we write down again T1 and T3 in terms of the displacement field using this relationship again. But you have to be specific to the surface by using different n, because you can see that even though T1, T3 and here, we use the same expression, but n are different for the two surfaces, right? You have to be specific to the surface that you deal with here, okay? N are different, okay? For the surface S3, S4, S5, and S6, we can do exactly in the same way as S2. Okay, you can see that the prescribed information of the traction is still the same, right? Right. You can see that the same as the previous formulation, but the only thing that different is here, right? Okay, because we have to express traction in terms of the displacement field. So now, if we provide the formulation like this, without this one, it's not complete. And without B, it's not complete as well. So I need to provide information like this. Oh, I forgot to mention here as well. If you provide this one, it's still not complete, right? Because you know that, okay, I didn't give you mu and lambda, if you remember. I mentioned about that at the beginning, right? So we know Poisson ratio and Young modulus. So I need to express mu in terms of E and Poisson ratio, and the same for lambda. So if I provide this information, now I know the value of mu and lambda because I know E and Poisson ratio. So this relationship are important too, to make sure that, okay, you have the complete information. And the last part, I need this relationship. You need to tell people how traction is connected to you, because if you don't know that connection, there's no way to check this kind of boundary condition. You know that, okay? Once you get U, how can you check if you don't have the connection between T and U? Okay, so this is the complete formulation for the displacement based case. Okay, do you have any question about anything here? No? Okay, so let's move to the final formulation. If we look at stress-based formulation, now if we shoot the stress at the key unknown, now we have to use Beltrami-Michel equations, right? At the Covenant equation, at one of the Covenant equations, because the problem that we focused on here is isotropic, right? And the body is made of isotropic material with constant material properties. So I can use Beltrami-Michel equation. And you know that for the case that we focus on here, we know that the body force is constant, right? Gamma is constant. If you remember, for constant body force field, Beltrami-Michel equation can be simplified, right? You know that? Okay, so this is a general Beltrami-Michel equation because B is constant for this case. So that term disappear, and that term disappear, and that term disappear. So now we can say that this one equal to 0, okay, because the body force field is constant. So the equation is simplified a bit here, okay? So now we are ready to formulate a problem like this. So we want to find the stress field sigma. The satisfy, don't forget that for the stress-based formulation, stress is not, we require not just to satisfy the Beltrami-Michel equation, we need to make sure that stress is in equilibrium with the body force field. So in this formulation, we need to satisfy two sets of equations. The first one is the equilibrium equation, and the second one is Beltrami-Michel equations. And for this particular case, term involving body force field is eliminated, right? Because body force is constant. And this equation has to be satisfied for every point X in the body. And also I need the boundary condition as well. Okay. For the surface S1, this is the difficult part. Because for this surface, we know the displacement field. We know the displacement, right? But stress is a key unknown. So we need to have the connection between stress and displacement. So then I write down U1, U2, and U3 that you have to verify with the prescribed value. So you have to express that as a function of sigma. I will leave this like this at the moment. I'll come back and talk about this. So now, if let's say that, okay, you can make the connection between U1, U2, and U3 with sigma. Then you have to verify that with the prescribed value like this for the surface S1. For the surface S2 is simple. Okay, this is similar to the first formulation because if you take a look that traction can be expressed in terms of sigma, right? Using Cauchy formula. So I can express or I can connect traction with sigma directly. Okay, so you verify like this. Okay. And for S3, I do exactly the same way, okay, for the first and for the third component as a surface X2. But for the second component, I do in the same way as the one that I use for S1, okay? For S4, S5, and S6, okay, I use exactly in the same way as S2 because the traction are prescribed, okay? If you compare with the second formulation, this part is different, right? You can say that we express traction in terms of stress, but they are the same as the first formulation because stress here is the key unknown. I need to provide more information like this. I need to provide body force field because body force appear here as well. You can see that. And also I need to provide this relationship because the traction is not the key unknown, but we can relate that traction with stress using the Cauchy formula like this. So if you provide this information, people will know once you get stress, now you can connect, you know, once you get traction in terms of stress, now you can verify this condition, right? Okay, you can compare with the value that prescribed. Okay, the only problem is the first one, the first surface, because how can we connect the displacement with stress? This is quite difficult, but we have a way to connect that. So if let's say that the case stress satisfy this equation first. Once stress satisfy Beltrami-Michel equation, now you can always get the displacement based on this flow. Okay, one stress is obtained here. Now you can get strain. And then you can integrate strain displacement relationship to get displacement field. and then you can use that one to check the boundary condition. So for this formulation, if you have part of the boundary that you know the displacement field, you cannot avoid doing this. Okay, you need to connect between displacement and stress, and this is the more difficult part of this formulation. But if the problem that you deal with, you don't have the displacement boundary condition, that is simple because traction can be related to stress directly based on the Cauchy formula like this. Okay. Do you have any question?
Yes, Ajahn, on JustWorks.
Can you say again? I cannot hear you.
I write in JustWorks, Ajahn.
Can you ask your question here?
Yes, I'm still confused about when in the final form I have to present. I mean your example just prep and depend on it, we have to build the formulation follow initial condition, Ajahn.
What do you mean initial condition? This is not dynamic problem, so we don't have initial condition.
No.
So we have only the boundary conditions, okay? And yes. And when you try to formulate the problem, you have to be specific with the information that I gave you, because the formulation that you will use here, that you will get here, you will use that later in solving problem. So the information that you provide in the formulation have to be specific to the problem that you are interested here. So the formulation that I gave you here, you can see that I try to connect with the information of the given problem. You know what I mean, right?
Yes, Ajahn.
Okay. Is that clear?
Yes, I think so.
Okay, we can discuss in more detail if it's not clear. So you can discuss with me later after the class. Okay.
Yes, Ajahn.
Anything else? Okay, we're done with the first lecture here. So I will move to the second lecture about work and energy principle. I will give you a break here for 5 minutes. I will come back. So try to download the lecture note from my course field. I will come back in 5 minutes.